the asymptotic distribution. Now, the large sample properties of maximum likelihood are the ones that are usually discussed and relished. So, the large sample distribution, I will change the mu symbol here, it is a typographical error, it should be mu. Normally, the distributions are written this way, root n times mu minus mu naught, or root n times theta hat minus theta naught, right, where theta naught is a true value. Why do not we specify simply theta hat, the distribution for theta hat asymptotically, right? Why can't we talk of this? The reason is, as n goes to 0, sorry infinity, if the estimator is consistent, then what happens to theta hat? It converges to the truth, and the truth is deterministic. So, what meaning does it have to write the distribution of theta hat as n goes to infinity, right? So, for example, if you take sample mean, right, y bar, we know the variance of y bar, it is an unbiased estimator, it goes to 0 as n goes to infinity. So, there is no point in asking what is the distribution of y bar for large samples as n goes to infinity, because then it clearly says y bar is unbiased estimator, variance of y bar goes to 0, which means y bar will go and settle at mu, which is a fixed quantity. You can't generally think of, you can think of distributions, but it is a singular, the distribution becomes singular there. On the other hand, if I look at root n y bar, root n y bar has a variance of sigma square, right, because if y bar has a variance of sigma square by n, assuming that the data falls out of Gaussian uncorrelated process, then variance of y bar follows sigma is sigma square by n, and therefore, variance of root n y bar is sigma square. Now, root n y bar is a random variable in its own right. Now, you can ask what is the distribution of root n y bar as n becomes very large, right, and that is why the distributions are specified in terms of root n theta hat. Of course, you can give either in terms of root n theta hat or root n theta hat minus theta naught, the choice is yours. That is only to tell you that you are doing it some kind of a mean shift distribution in terms of shifted estimate with respect to the truth. So, it says that the ML estimates of mu hat, we know already sample mean follows asymptotically Gaussian distribution with root n y bar following sigma square, and it says asymptotically, we have just seen that in the case of variance estimate, the estimate follows a Gaussian distribution as n becomes large, and the fact that the sigma square root n sigma square hat minus sigma square, you can read as sigma square naught, has a mean of 0 means that it is an asymptotically unbiased estimator, and this root n sigma hat square has a variance of 2 to the sigma power 4. Okay. You can check that. In fact, for the problem that we have done, we can ask, so what according to this expression, the variance of sigma hat square is 2 sigma power 4 by n, right. Remember, the variance of root n sigma hat square is 2 sigma power 4. So, variance of sigma hat square would be 2 sigma power 4 by n, right. So, let us look at that. Now, we can ask what is the variance of the Parest, the second one, which is the variance of the sigma hat square, and it says 0.145. Now, we can compare with the theoretical result. The theoretical result says this variance should be 2 times the true sigma power 4 divided by n. The true sigma is 2 because we have used sigma square as 4. So, 2 times 2 power 4, which is 16. So, we said 32 by what is n? Pretty close, right. In fact, as n becomes large, those values will match. Okay. So, you should of course remember, as we have just discussed, that the finite sample distribution of sigma hat square is a chi-square distribution with n degrees of freedom. In this case, when you use 1 over n minus 1, it has n minus 1 degrees of freedom. Here you have n degrees of freedom. That is the difference. In least squares estimate of sigma hat square, you are losing 1 degree of freedom, because you are going through a 2-step procedure. You are estimating mu, you have used up, it is like n independent observations or n boons given to you. You have used up one of the boons by the time you have come to estimate sigma hat square, whereas MLE is estimating simultaneously. So, both mu and sigma hat square are using the n observations. Okay. So, that is a difference, but there is a bias, remember. And as I told you earlier, one of the advantages of maximum likelihood formulation is that heteroscedasticity. What is heteroscedasticity? Variance changing with observations. Your data is not necessarily falling out of, it may fall out of the same family, same mean, but the precision can keep changing, and this can happen. Suppose your data is coming from different sensors of the same variable, and then you are trying to fuse that data together. So, I have let us say 10 sensors for measuring a critical variable such as a temperature in a nuclear reactor. Then each sensor has its own precision, and I want to fuse all this 10 sensor data to get an estimate of the mean. Let us say that is what, and I am given the precision of each of the sensor, it is important, otherwise you can't estimate it. So, let us say that k here does not represent the observation, but k represents the sensor, right. So, sigma square k is the error variance associated with the kth sensor, and assume it is known. Now, all you have to do is go back to your log likelihood, nothing changes, go back to your log likelihood and absorb this here. So, now theta 2 is not fixed, in fact there is no theta 2 because only one parameter. We are saying there is mean, I want to estimate the average given of the temperature, which is the same variable, but the readings are obtained from different sensors, and I am given that each sensor has its own precision or its own error variance, right. Now, intuitively, if you were to look at the average, if you were to average such data where each observation is coming with different precision or different error variances, you do not want to apply a simple average, because simple average assumes that it gives equal importance, it is 1 over n sigma yk, it gives equal importance to each observation. But now I have to give different importances, because one sensor is more reliable than the other, it is more precise than the other one. So, how do I, what is a measure of precision? 1 over sigma square is a measure of precision of a random variable or of any measurement of a coming from a sensor. So, obviously now I will construct a weighted average, and intuitively these weights would be inversely proportional to the sigma square of that sensor. So, it turns out that when you change, make the necessary changes in the log likelihood, you have only one parameter, theta 2 is no longer there, it gets goes into the log likelihood function here, and what you have instead is, apart from the other two terms, they are going to be constant. The only term that would be of interest would be yk, sigma yk minus theta 1 to the whole square by sigma square k. Now, you can't take sigma square k out of the summation, unlike what you do in least squares. So, if you were to work with least squares, it would ignore the different precisions, ordinary least squares, it is called ordinary least squares, we have mentioned that, right, and it would give you sample mean as a estimator. There is nothing wrong, it is still unbiased, but it has much larger error possibly than the estimate that you get by minimizing this. Now, this will be the case, whatever I have written here will be the term that you will optimize, whether it is log likelihood or whether it is least squares. If you think of this as a least squares problem, then we call this as a weighted least squares formulation, where the weights are chosen inversely proportional to the precision. And of course, as I said, we assume sigma square k's are known, and all you have to do is now differentiate. So, this is your L of mu given y n. you are going to minimize this negative log likelihood, right. In fact, sorry, this is log likelihood. If you take the negative log likelihood, the negative sign vanishes, and then if you minimize with respect to mu or theta 1, then you get this solution, which is the same as you would get with weighted least squares. Again, beautifully what has come out is, when there are heteroscedastic errors, MLE naturally takes that into account, and of course, the least squares fans, that is, there are people who really vouch for least squares, they can say that I can set up a weighted least squares. Yes, they are equivalent, but you see in weighted least squares you have to take this additional step, you have to figure, you have to argue that the optimal weighting is 1 over sigma square, whereas optimal weighting has been naturally taken into account in MLE, right. So, weighted least squares formulations are very, very popular, and what we have seen just now is that it is also a special case of MLE, when the data falls out of a Gaussian distribution with heteroscedastic errors. So, the ML formulation also encompasses the weighted least squares problem or formulation. So, just to summarize now, the general procedure for setting up an MLE, assume a density function if it is not given to you. If it is given to you, merrier is the situation. Go to step 2, construct the likelihood function, which is usually the rate limiting, the effort demanding step, depends on whether your observations are correlated or independent, and so if they are independent, life is easier. Of course, here when I write here xk and vk, this is usually for a deterministic case. You can ignore this for now, you can say, just say putting together basically the everything, the correlation and so on, you can set up the density function for y and hence the likelihood. And now you can solve the optimization problem, as we have seen, you do it in R, that is it, right. So, you set up the likelihood function. In fact, a lot of times you can do it numerically also, and there are some smart tricks to make the likelihood function, even the log likelihood function, amenable to optimization, so that the optimizer does not have to spend too much time finding the optimum. That I will leave it to you to search through the literature. For some high dimensional problems or large scale problems, you may have to be smarter in writing the log likelihood function in a particular manner. And remember, in order to carry out the last step of optimization, the PDF has to satisfy so called regularity condition, which means that essentially it should be first differentiable, and regularity also means that you should be able to change the order of the integration of the PDF and the differentiation of the PDF. In this case, we have not integrated, but there are further analysis which requires integration of the PDF, because if you are examining for the bias of the estimator, for example, then you are going to evaluate the expectation of the PDF or the likelihood, which means that will involve an integration. So, a PDF is said to be regular if the operations of differentiation and integration can be interchanged. When the PDF is not regular, the derivative of likelihood generally does not exist, and then the optimum has to be determined by inspection. This happens with the uniform distribution case. And since ML is a nonlinear optimization problem, you have to watch out, multiple solutions may exist, it may get stuck in local optimum. So, you need a good optimizer that pulls out of pulls the function optimizer or the function out of the local minimum or maximum. And finally, you want to compute the errors. I have shown you the Monte Carlo way of doing it, I have reported the theoretical ones. Since MLE almost always is a nonlinear estimator, generally it is not possible to come up with analytical expressions, but remember the asymptotic expressions that I have given hold, and we will just quickly talk about asymptotic properties and then we will wind up with some remarks on computational. That will close the computational aspects of MLE, and that will close the lecture on MLE. So, generally the asymptotic properties of MLE have been studied very well and are reported in the literature. The small sample properties, as you have seen, are not so attractive. So, the first property of interest, as we know, is consistency. We want to be guaranteed that the maximum likelihood estimate converges to the truth, and it does converge in probability. So, it is not such a great guarantee, because we know that convergence in probability is the weakest form of convergence, but it is okay. In some cases mean square convergence is guaranteed, in some other cases almost sure convergence is also guaranteed, but in general the guarantee is for convergence in probability, that is what this statement says. And then asymptotic normality, always large sample estimates coming from MLE, does not matter what parameter you are estimating, it follows a Gaussian distribution. And of course, here I have not written root n, and that would get absorbed in this quantity which is known as the inverse of the Fisher's information. So, what this equation says is the estimate, the parameter estimates coming out of ML follow a joint Gaussian distribution with mean theta naught, right, that means asymptotically unbiased, and variance given by I of theta inverse, I n of theta inverse. This is I of theta, which we have not discussed in this course, is called the Fisher's information. Since we have not discussed in this course, let me just tell you that Fisher's information and there exists another result called Kramer-Rouse inequality, the estimation literature. Putting together, you can interpret Fisher's information as the best precision that you can achieve for a given estimation problem, assuming that you are going to use MLE and so on, but Kramer-Rouse inequality essentially says that the Fisher's information matrix I of theta here has the same dimension as sigma theta hat. Remember, if you are estimating p parameters, sigma theta hat is p by p. And what does sigma theta hat signify? It tells me what are the errors in the parameter estimates. Of course, since you are estimating jointly, we look at the variance covariance matrix, but the diagonals of it can, square root of the diagonals of sigma theta hat will give me approximate errors in the respective parameter estimates. So, suppose I ask what is the lowest sigma theta hat that I can get, then the answer is I of theta inverse. That is, no other method can get you lower error than what the maximum likelihood estimation can get you asymptotically. If the ML exists, then there is nothing to beat it, that is what it says. That means, if your PDF is regular and you are able to find it, find the optimum, global optimum, then there is nothing like it. That is a fantastic and a very, very powerful result. It gives a lot of support to the use of maximum likelihood estimation, but all of this is asymptotic properties. So, think of Fisher's information as the best precision matrix for your theta hat. Of course, here I of theta here is being evaluated at theta equals theta naught. I of theta in general can be a function of the parameters. So, this Fisher's information matrix computation is again based on the notion of likelihood. I am not going to dwell on it, but in general it is a function of theta, it can be, and for this problem here the best possible precision is found by evaluating the Fisher's information matrix at the true value. Of course, you will not have the true value in practice, you will use theta hat as a proxy for theta naught. Okay. So, the summary of this point here is that 1, the estimates follow a joint Gaussian distribution, the ML estimates, and that they are the most precise as n goes to infinity. That is enough to remember. Then asymptotic efficiency, we have already spoken about that. In fact, it is a corollary of what we have just discussed. We have said that ML estimates are they are obtained, they are the most precise estimates, which means they are the least error, and therefore, they are the most efficient asymptotically. So, there is nothing more to talk about that. Of course, there is Kramer-Rouse inequality to give you the support and so on. We do not have the time in this course to ponder on Kramer-Rouse inequality. We can, of course, you can ask questions on the forum and I will be able to answer that. And then naturally, from the previous result we know ML estimates are asymptotically unbiased. So, we will not expand further on that. Now, this is a very important and interesting property of ML estimators, which is invariance. What this means is, let us say I am estimating sigma square. Now, someone comes along and says I want to estimate sigma. So, in one case a parameter is sigma square, in the other case a parameter is sigma. Now, it is not necessary that in with any estimation method, the estimate of sigma is the square root of estimate of sigma square. Okay. It is not necessary that sigma hat is, that is optimal estimate. Optimal estimate is not necessarily this. This is not necessarily true. However, with the maximum likelihood it is true. So, maximum likelihood estimation method says whether you estimate sigma square and take the square root, or whether you estimate sigma, you will get the same. You can check, but of course, what happens in R is that you are not going to get theoretical optimum, right, you are going to get numerical optimum. So, they may differ slightly. That means, step scenario 1, you want to estimate sigma square like we did in the R script, do it, take the square root of that, hang on to that, store it. Now, you estimate, now you go back to your R script and say my parameter is sigma, not sigma square, rerun your code and compare the estimate of sigma with the square root of the estimate of sigma square that you computed earlier. They should be very close, okay, and that should be the case. In fact, with large n you will be able to see this closeness. So, this is a very interesting and important property of maximum likelihood, which is not, which does not necessarily hold with other estimators like least squares and so on, and that is about it. So, those are the glorious properties of MLE that makes it a star in the world of estimation methods. Finally, I just want to make a few remarks. I am not going to talk about these things in detail, because we have talked about computational aspects. There are, it is a nonlinear optimization problem. So, all the standard nonlinear optimizers can be used, yet there exist some specialized algorithms for computing the optimum for MLE, because of the nature of the log likelihood. These algorithms can exploit those features of the log likelihood. So, Fisher had his own scoring method, for example. It is a variant of the Newton-Raphson method. You know, Newton-Raphson methods are used for solving nonlinear optimization problems. Then there is a polytope method where a simplex method is used, but this simplex method is not the one that is in linear programming. You can refer to this paper here, where some kind of a heuristic direct search method is used. Optimization is all about searching for the optimum, right. So, there is gradient search algorithms, there is steepest descent algorithms, there is so many different kinds of algorithms, Levenberg, Marquardt and so on. This is one kind of a direct search methods, and is also known as simplex method, not to be confused with the one in the linear programming world. Then you have the very famous and celebrated expectation maximization algorithm, EM algorithm, which was originally developed for, I mean it is now being used by and large for performing maximum likelihood estimation in terms of missing observations. So, there are two steps in this EM algorithm called the expectation step and the maximization step. So, the expectation step is the case where you fill or you impute the missing values with the best estimate, the conditional expectation, and maximization is the maximization of the log likelihood. So, you do this in iteration. You first impute the values of missing observations by using the data that you have and the PDF that you have specified, and now the data is complete, and then you run the MLE on the complete one. Use these parameter estimates, go back and recompute the conditional expectation and iterate. So, that is what is the EM algorithm, largely due to Dempster, Laird and Rubin. You can actually refer to the literature for EM algorithms. Of course, it does have its own problems, it may not converge to the ML estimates and so on, but if you want further technical details, you can read either the book by Shumway and Stauffer or this other reference here. Okay. So, that completes the lecture on maximum likelihood estimation. Hopefully, you got a good taste of the method, and the R illustration gave you some confidence on being able to take the ML theory into practice. In the next lecture, we are going to look at application, that is we will start with hypothesis testing and so on, and then hypothesis testing and probability density function or density function fitting, and then linear regression. In fact, we have already covered the aspects of density function fitting. This entire lecture was on that using MLE. Then we have talked about linear regression to a great extent in least squares. What those lectures will do for us is they will focus more on application rather than the method itself. So, we will take some case studies there and then talk about how to illustrate how to do that in R. So, the focus will be more on application, illustration in R. We have already talked about the methods that we are going to use, but we will begin first with hypothesis testing, because that is central to all other applications that you see, whether it is density function fitting or linear regression. And in hypothesis testing, we will use the idea of confidence intervals, which we have discussed earlier. All right, folks. So, until then, see you and have a good maximum likelihood session.